So this will be a session which is a part of the Orbs contributor guide. And it will talk about Go concurrency because a lot of what we're doing in Orbs right now, the reference implementation, the most recent one, is written in Go language. We think Go is an excellent language for blockchains. That's why we work with it. And Go has a few interesting concurrency patterns that we should reason about just to get a hang of the code and how it works. Okay, so before we jump into how Go works, let's list some of the popular concurrency patterns or models that you're familiar with in other languages. Okay, so one of them, for example, is threading. So if you wrote code in Java or in C++, you probably are familiar with threads. So I'm not going to go much into threads right now. I'm just going to assume that you know them. What other concurrency models you have? So for example, if you come from JavaScript or you wrote backend code with Node.js, then you know that Node is a single-threaded system. So you still need to reach concurrency on that system as well. And in the JavaScript ecosystem, it is done using an event queue. Okay, event queue lets you do lots of promises and callbacks and async await and stuff like that, which is just a different model. Then we have the world of green threads or fibers, which are kind of user mode threads. That means that there are threads that are not operating system threads, but another abstraction, cheaper abstraction on top, which may be cooperative and maybe not. It depends. I think that's a difference between green threads and fibers. And there are languages that like this model, for example, Python, green threads is very popular there, and Go is almost entirely built upon this model. There's also a model that I personally haven't worked with a lot called actors, used in languages like Scala and Erlang. Maybe Shai, you want to say a sentence about actors in concurrency?
Actually, an actor is just a different way to do concurrency. It has a mailbox, which is kind of a queue, and some code that takes stuff from that mailbox and processes it. Actually, we can achieve something very much like actors in Go if we use a Go routine and a channel for input from that Go routine.
Okay, cool, awesome.
And actors originated in Erlang. So like Erlang invented was the first language to implement the actor model, and then in Scala it's very much based upon what's done in Erlang.
Okay, so I got the languages right. Okay, so let's jump into Go routines. And Go routines are the green threads or the fibers used in Go language. And they're very similar to threads that you're familiar with. So they have a few benefits. So Go routines, yay. I think the main benefit is that Go routines are very cheap. Okay, an app can run literally millions of Go routines. Okay, there's a popular talk by Google. I haven't seen it, but I heard about it, that they actually, in production, debugged a system with 1 million Go routines live. So you can actually, yeah, so maybe I think it's one of the talks that Shai organized in the future. So we'll see it. So that's one thing. In threads are pretty expensive. That's a problem. If you try to run on a system a few tens of thousands of threads, the system's going to start choking. Scheduler has a hard time running all these threads. They take a lot of memory, a lot of non-paged pool kernel memory, which is very expensive. So lots of threads is problematic. That's why many of the web servers that you're familiar with, for example, Apache, can't really scale. Another great thing about Go routines is that they're very easy to set up. Only takes 2 letters to start a Go routine, and threads usually have some boilerplate to start them. But they're not all perfect. For example, to have a Go routine system, Go has to implement internally a very, I don't want to say complicated, but a rather deep abstraction layer above the operating system. And this is not fun to work with. For example, if you ever tried to port Go code to mobile, there is a Go for mobile SDK, and it kind of tries to implement the entire fiber system or Go routine system on mobile, and it does not work very well. So that's one of the issues with this. With threads, one of the great things is that every decent operating system supports them natively. So let's see a very simple example of how you use a Go routine. So let's say I have a long-running function, HTTP print weather.com. And it's a long-running function because it's going to do an HTTP get. It's going to take 5 seconds, and it's going to print a response. So if I run this function directly in main, which is the first line of code you see on the left, then you will just block for 5 seconds until the whole thing finishes. Now let's say I want to do other things, so I can just run it in the background. Can you open Corianta? Okay, we're recording, so let's do it seamlessly. So if you want to just run this same function on its own Go routine, all you have to do is just add 2 letters, Go beforehand, very, very simple. Okay, so now one of the first questions people ask is, which operating system threads host my Go routines, right? Because Go routines are an abstraction above the operating system. And the answer is, you're not supposed to know, okay? You don't care. It's an internal implementation detail. It depends on many runtime environment things. For example, the configuration. Okay, you can configure Go to use different amounts of active threads for the Go routines. I think it varies on operating system. It varies on the CPU that you use and the number of cores it has. And I think it can also vary on the load of the system at any given time. So you can't depend on that. So basically what you have to do is plan for the worst. What does it mean? Assume that everything is running at the same time. Okay, this is, I think, the most complicated scenario to deal with in terms of synchronization. So always assume that all Go routines may run at the exact same time on different threads running on different cores. Okay, this is the most complicated scenario to deal with. This is usually not the case. Okay, they are scheduled, but I think it's better to assume it. So let's now tie this entire thing into Orbs. Okay, so if you want to be an Orbs developer, let's try to think about which Go routines do we have in Orbs. So one family is the long-living endless loops. Okay, for example, the consensus. Okay, the consensus flow, it's pretty much an endless loop that tries to close blocks. Okay, it tries to reach consensus over the blocks, close them, and write them to block storage. So this endless loop will get its own Go routine. We have another example in the transaction pool. Okay, we have a flow, a process that takes expired transactions every few seconds and deletes them from the pending pool and the committed pool. So to delete them in an endless loop, we'll just stick it on its own Go routine that just does it forever. Another example is the block storage block sync. Okay, we have an inter-node sync and an intra-node sync. We sync the services inside the node to the current block, and we sync others. This will probably be hosted on its own Go routine because it's a routine process that happens all the time. Okay, so I think this was the other example I talked about where block storage syncs another service. In here is the state storage, for example. It also syncs transaction pool. So all of this will be on its own Go routine. And last but not least, the public API. So we have a public API HTTP server, and it listens and serves. So this listen and serve needs to be hosted on a Go routine. And I think there'll be more. It depends on the system. Okay, so another family of Go routines that we have in Orbs is short-lived Go routines. And I think the most popular ones are incoming HTTP requests. So how does that work? So we have public API and we have an HTTP server, and the HTTP server listens for incoming client requests. And for every incoming client requests, the default HTTP server of Go creates a new Go routine to handle that client request. So this Go routine is short-lived. Why? Because the moment we finished dealing with this client, we terminate the Go routine. Okay, it's terminated automatically once we return. So it's very different. And also it may be canceled in the middle. Okay, imagine if the client, for example, disconnects. Okay, while you are trying to do a long computation for this client. So Go has pretty cool mechanisms, we'll discuss them later, that will allow us to kind of cancel the whole thing if we know and kill and terminate the Go routine, I think, in advance, before we finish everything. Another example is microservice incoming requests. Okay, so once we transition larger parts of the system to microservices, every service that is actually running its own server also will listen and serve for incoming requests, and that's the exact same thing. So every time the server will have an incoming RPC request coming to it, it will create a new Go routine to handle it, and this Go routine will be short-lived and terminate once we respond. Okay, and maybe cancel in the middle as well, exact same thing. So let's see an example, and the example is one I did with Ido, I think, in our pair session, and it's a nice example because it shows two families interacting, and our example use case is the following scenario. Okay, we have consensus context. Consensus context is the part of the consensus that knows the block format and everything. So this part of the system is trying to create a new block, to propose a new block for the consensus algorithm. So in order to do that, it needs to collect transactions from the transaction pool to populate the new block that it's going to propose. Okay, so this is the scenario we're talking about. So what are we going to have there? So CC, that is the consensus context, needs to request TP, the transaction pool. Let's say, just for the sake of this simple example, it needs exactly 100 transactions from the pool in order to populate a new block. So this request runs on a Go routine. Which Go routine is it? That is probably the consensus closed block endless loop. Why? Because every time this endless loop is trying to close a new block, then it will go and run this method on it. Okay, to tell consensus context, give me some transaction pool transactions. Now, what the problem? The problem is that the transaction pool only has 99 transactions. And let's say that the implementation dictates that we should block and wait until a client gives us a new transaction. So we can return exactly 100. Okay, so we're blocking the consensus. Now, in real life, we're not really blocking the consensus. We're going to have timeouts and everything. But just for the sake of this simple example, let's think that we want to block forever. So where is this running? Okay, so the blocking occurs on the same Go routine from before, right? It requests the transaction pool, and transaction pool is blocking. So now the consensus close block endless loop is blocked. Now a client sends us a new transaction. Okay, so this is an asynchronous process. And how does it work? How does a new transaction arrive to the transaction pool? It arrives on its own new Go routine. And if we look on the list before, this is one of the public API HTTP server client handlers, right? Because the client did an HTTP transaction to the public API. Public API gives this transaction to the transaction pool. So it's going to run on the same Go routine of the HTTP client transaction. So now we have two Go routines interacting, because once the second one is going to add the transaction to some synchronization mechanism, we will want the transaction pool to unblock the first Go routine and respond. Okay, so here that was just to give us a little bit of context. Awesome. So let's talk about, let's dive out of Orbs back to general Go discussions and talk about a few gotchas with Go routines. And one of the gotchas, and I want to start with gotchas because I think the concept of threading is pretty simple, and I think the fact that Go routines are pretty much just cheap threads makes it very, very easy, and we don't need to go over the syntax or anything, so we'll just dive into the more interesting parts. And I think the rest of the talk will cover these. Okay, all the, like the beyond average things that you need to know. So one area is panics. Okay, so panics in Go, I'll just remind you, if you don't know what they are, is normally in Go, error situations are returned from the function. But you have something similar to exceptions, which are exceptional situations. For example, errors that you don't expect and they're very hard to recover from. Those are implemented in Go in panics, okay, and that's exactly what it does. Okay, you shouldn't use them in your code unless you really are panicking. For example, I'm trying to allocate memory and there's no memory available. Okay, this is a good example for a panic. I'm trying to write a file and there's no hard disk space to do it. So panics usually go because you don't want your code to panic in production, even if you're running out of memory. So what Go allows you to do is to recover from panics. So basically how it works is that the entire stack kind of folds until somebody catches the panic and recovers from it. Okay, so you can have some sort of a top-level handler, very similar to finally clause or stuff like that from exceptions, to catch exceptions. So panics cannot be caught and recovered between go-routines. So the entire recovery mechanism that you need to have is per go-routine. Okay, and that is important because if you forget, like if somebody else writes a go-routine, you can't have a catch-all handler for your system. If somebody else in their code did a go-routine and that go-routine panicked and that person did not have a recovery mechanism, then it will die. And you probably don't want that in production, so you need to kind of like supervise and go over all the go-routines that you have. So if a go-routine panics and crashes, nobody will ever know about it. So this brings us to the conclusion that every long-living go-routine should have a top-level recover in some way, because if you need it to remain living for the system to operate, for example, the consensus, and it panicked on some crazy situation like no memory in one of the locations, you want to be able to recover from it and keep that go-routine living, or just restart the entire thing if the node cannot be recovered. Let's talk about lifetime of go-routines. So one of the interesting things is that the process that you run terminates when your main function returns, pretty much. Okay, so you always have like one go-routine, which is the main one, which executes your main function, and when this function returns, the entire process terminates. And it doesn't matter how many active go-routines you have in the system. Okay, this is unlike other systems that have in Java, for example, you can have threads that you can define them as to delay the shutdown of the process until they terminate. Daemon threads. Okay, so we don't have that concept in Go. So you need to be aware of that. That means that you need to implement a graceful shutdown carefully by yourself. So residual go routines between tests, for example, this is one of the areas that we hit it a lot, will keep running. And I'll give you an example. Let's say that we're testing the consensus process. And we said that the consensus process starts a go routine that runs in an endless loop. So basically every test scenario is going to start this long-living go routine. And once we move to the next test, unless we do an active graceful shutdown, this go routine will not be terminated. And it's very easy to have a bug that you move between tests and you have residual endless loops from old tests that are just screwing up the system. If they're printing stuff or failing things, they're going to add a lot of noise. So what you want to do is make sure that you terminate them somehow. One of the ways to do it is with a context, which is a concept that we'll discuss in the next few slides. Okay, and this is a meme from Shai. Okay, one does not simply start a Go routine. And this has to do with long-living Go routines. Okay, they need their own set of things. When you have a long-living Go routine, you need some sort of supervision mechanism to monitor them, restart them on panics, and so forth. And you usually have to implement it yourself or rely on a library. Shai discussed, for example, Suture is a library that he liked very much, and we might introduce it to Orbs in the future. So the tip is, number one, recover on the top level, or use a library that does it. And number two, rely on a context, which we'll define what a context is a little bit later, and terminate this Go routine when the context is canceled. So we're going to see how to do that. Another gotcha for Go routines is creation order. So let's take a look at this code. So what this code does is it takes just a simple loop that prints the number in new Go routines for all of them. So what do you expect? What do you expect to be printed? And their answer is, expect nothing. You have no guarantees on the order of the prints. Why? Because it's an implementation detail on when each of the newly created Go routines will be scheduled. And you don't know how the scheduled works, and the scheduled does not specify that it runs initially Go routines in the order that they were created. Okay, so for example, we have an active bug caused today in the tampering gossip exactly because of this issue. Okay, what we have there is many Go routines of the receives, and when they are unlatched together at the same time after we pause them resumed, all the Go routines run at the same time, and we get them in different random orders and flaky orders. So this is exactly a cause of flaky test, for example, in our case. Okay, another gotcha. So I showed you one. Okay, let's say that this is one of the services that you implement, and you have your new service, and this service has a variable that holds, for example, all the blocks. Okay, this, for example, could be part of the block storage. So we have an array. It's very simple in memory, just for the sake of simplicity, and we have on our service a slice of blocks. And we have a function that our service, an RPC function that our service responds to called onCommit that other services call, and when a new block is committed. And all we did is just we append the block. Okay, so what's wrong with this code? Anyone? Not all at once? Okay.
You need to protect the...
Exactly. So it's not synchronized. Exactly. So you need to be careful. You have no guarantees on who, on which Go routines, on how many concurrently the onCommit is running, and if it's touching a shared variable, it needs to be protected. So it kind of brings us back to the entire world of pain called synchronization. That that's one of the main drawbacks with threads, that you have to synchronize them. Okay, that's all the pain in Java. But synchronization is important, and even in other concurrency patterns. For example, like the event queue of JavaScript, people think that synchronization is easy and simple and you don't need to do it. And in most cases you don't, but you still need to do it in some cases. And we can show you examples of async await that will completely corrupt your system because they're not synchronized. So you need to think of synchronization mechanisms almost everywhere, and in Go is specifically. Okay, kind of like in the regular threading model. So always stop and think about synchronization. Every time you write something, always put a hat on saying, okay, how is this synchronized? Where is this running? And make sure you have good answers. So let's go for a few pointers. For example, every access to a shared variable that may be accessed at the same time from multiple Go routines must be synchronized. Atomic operations. If you have an operation that you expect to happen atomically, you need to synchronize it. If you have transactions meaning several operations that need to happen in order and as a batch, and if one of them fails, you need to undo the other ones. So this is an operation that requires synchronization. Race conditions between asynchronous operations is something you need to think about and synchronize. And last but not least, deadlocks, live locks. You can reach situations where you're blocking and everybody's blocking. Go handles these very nicely, actually. That if the system reaches deadlock, you will get a nice panic from the system, from the runtime, that will help you debug. So let's go over the main Go synchronization primitives that you should be familiar with. So the first one, and the most popular one, is channels. Okay, channels are the main synchronization primitive used in Go to make sure the different Go routines are synchronized. The second most popular synchronization mechanism, can anyone guess?
MUTEXES.
No, channels as well. Okay, always use channels. I think that is the bottom line. Like 90% of the time, you should use channels. MUTEX is the next one, and MUTEX comes together with read-write MUTEX, its friend. We're going to go over them in a few seconds. And I think the third popular one is cond, and we'll go over cond later on. And there are a few others, not many. I think like 2 or 3 others. They're all found in a package called sync in a standard library, and make it a habit just to familiarize yourself with this toolkit, and just go over the Go docs for sync package like 3 times, just to make sure that you know everything there.
There's another sub-package called Atomic.
Atomic, that
inside sync that has atomic variables, which is something that you might need to consider if you need some atomicity in your set operations, for instance.
Mm-hmm. Awesome. Cool. Good. So now let's cover channels. And again, I don't want to go over the basics of what channels are. I assume that this is, I don't want to say basic knowledge, but just Google it, see how to work with a channel. It's very simple. So I'm not going to explain channels, but I'm going to just give you, I think, the 3 tips of making the most out of channels. Okay, so regarding channels, to know everything about channels, you pretty much need to know three things. So the first thing you need to know about channels is that channels can be buffered. Okay? So by default, the channel is blocking in both directions, meaning that if you have a writer, okay, channel, you have a writer and a reader. Okay, somebody can write to the channel, somebody can read from the channel. So the writer is blocked until some reader actually reads. Okay, this is the default behavior, and on the other direction as well. If the reader reads first and there's nothing in the channel, it is blocked until the writer actually writes there. Okay, this is why it's a synchronization mechanism. That's the idea. Okay, it's a rendezvous point. But sometimes you want to change this default behavior, and you can change it by adding a buffer. So a buffer, which is always fixed to some, Go does not support an endless buffer, which is a shame. I think I saw a few endless buffered channels implementations that people made. But normally you can have just a fixed size buffer that will allow you to have exactly n writes that are non-blocking. And how will that change? Once you add the buffer, the writer, when the buffer is in full, is not blocked. Okay? It will just write and continue running, and the write will go into the buffer of the channel. The writer, when the buffer is full, is blocked until the reader actually reads. Okay, which is exactly the behavior that we had before in the unbuffered channels. And the reader is always blocked. Okay, so the reader doesn't change. Reader is always blocked until a writer actually gave him something to read. Natural.
As long as the channel is
empty. Is live, exactly. So channels can be closed, that is...
No, but as long as the channel is empty. But if the channel is not empty, then the reader is not blocked. It pulls from the channel until it's empty, and then it's blocked.
Yeah, so a writer actually wrote before, so you have something to read. Exactly. Second thing you need to know about channels is that channels can be closed, and closing channels is not just a cleanup thing, it's actually a very convenient synchronization mechanism by itself. Why? Because you can close a channel at any time, and okay, so what happens if you have a closed channel? A writer that writes to a closed channel will panic. I think that it isn't very interesting, not very useful, just a protection mechanism. But this is useful. All blocked readers will unblock the moment the channel is closed. And since they don't have anything to read, if they had something in the channel, like Shai said, they would just read that something. But we're assuming that the channel is empty, because that's why they're blocked. So when they're unblocked, they're going to read the Go zero value. Okay, so zero value is a concept in Go. For strings, it's empty string. For structs or pointers, it's nil. For numbers, it's zero. So it's going to read the zero value. And this is very useful. Why? Because you can use this trick to have some sort of a broadcast that an event happened. So how would that work? You would have, if you want to have a simple event mechanism, you have listeners. So all of these listeners will try to read from the channel, and they will block because the channel is empty. And what you will do is, if you want to notify one of the listeners, then you will just write to the channel. So if you have 10 listeners, randomly one of the 10 will unblock and get that value. And if you want to notify all, which is the interesting feature, you just close the channel. Once you close the channel, they will all be unblocked. And this is very useful. You can use this primitive as a building block to build your own more complicated behaviors. And I think this is the idea in Go synchronization. You take the primitives that Go provides you, and you wrap them in your own more complicated logic that will give you more complicated, they're not primitives anymore, but structures for synchronization that you build yourself. But they will always rely on a primitive, and the closed channel primitive is an excellent primitive because it's the only one that allows broadcast. Okay? It's not really the only one. I'll discuss the second one in a second. Another cool thing you have is the range operation that you have in Go. Just like you can do a range, a for, and go over all the keys in a map or all the variables in all the elements in a slice. You can do the same thing with a channel, and you can range read from the channel, and it will just give you everything the channel has until it's closed. Okay, it's just basically a for loop until the channel is closed. Also very, very useful. And the third thing you need to know about channels, non-trivial thing, is select. Okay, and select is crucial in Go. What is select? Select is just like the original Unix select that allows you, you work with sockets with select. It's kind of the same thing. So select, pretty much, it stems from the idea that only very naive implementations block forever. Okay, usually production systems can't block forever. So what happens? How you do something in production? Okay, so the idea is that you always read and you block from multiple channels, and you can act when the first one responds. Okay, so you're not blocked forever. You're blocked until the first one unblocks you. And how would you use this? Okay, another small gotcha, that if multiple ones respond together, you don't know which one will be called. It's random. So don't make any assumptions on ordering. And this gives you a production pattern from reading from a channel. Okay, if you just read from a channel, you could have a leak, a Go routine that is leaked, a Go routine that will never be terminated because it will block forever. And this is usually something that you don't want in production. So you always want to have some sort of deadline that you block until it happens, because what you're expecting may not arrive. And the idea is that you would have one main channel that you actually need for your business data. Let's say we're trying to, let's take the example from before. We had the transaction pool waiting for new transactions in order to respond the 100 that was requested from it. So this would be some sort of a channel that collects until we have 100 transactions. So this would be the business logic. And it may block forever. Second one is a channel with a timeout. Okay, it's very reasonable, for example, in the consensus, that we give a timeout to close a block, and if we don't have enough transactions within these timeout, we just want to continue. And this can be done by opening another channel for timeouts and doing a select between the two. The time library, in the standard library, the time package, has several very convenient auto channel creation functions that create a channel and write to it when you want. So you can do time after, and time after just writes to a channel that it creates after some time passes that you can specify. And you have new timer and new ticker, which are a little bit more complicated things that you can use that do the exact same thing. They write to a channel in an interval. You can use them for timeouts. And another important one is for graceful shutdown. Usually, if you have a system, that system can be shut down, and you want it to be shut down gracefully. You don't want to kill all the Go routines. So if you can block, and let's say somebody wants to terminate a node before the timeout occurred and before the business data arrived, then you want to still end and terminate everything quickly. So it makes sense to have one channel for graceful shutdown. This can be implemented using a context. We'll cover that in the future, in a few slides. Okay, so this is the three things you need to know about channels, pretty much. I think one of the great things about Go that it's simple. You don't need to know a lot in order to know everything. Let's cover mutexes real quick. Mutexes are very simple. Just a simple mutex that can be held by one blocker. It just has two functions, lock and unlock. And this is the classic pattern for protecting shared variables. Okay, you just protect them with a mutex. So mutex lock, and the easiest way to do it, like the foolproof way, is let's say you have a function, and this function accesses shared variables. So you just follow this recipe. On the first line of the function, you do mutex lock. And on the second line of the function, you do defer mutex unlock. And this is great. Why is this preferable instead of just unlocking when you finished? Because you don't know what's going to happen. You might have errors that are returned, and if you need to go into every error returned and just unlocking the mutex there, it's just very error prone. You're going to forget one and you're going to add a lot of mess. Or what happens if there is a panic in the middle? Okay, for example, you run out of memory. So if you have a panic in the middle, then you would not unlock the mutex. Okay, and other Go routines that have not panicked will not be able to continue running. So defer is also running during a panic, which is great. So always do that, and always put your defer exactly on the next line of when you acquired the lock. So it's a very easy pattern to follow. Okay, you acquired the lock, make sure you free it. Locking twice.
Just one note about that is, of course, you need to remember that between the lock and unlock, you need to do as few operations as you need. So if like a good pattern would be to have a setter method that only changes the variable, and it has lock, defer, unlock, and then set the variable, and then any like heavy lifting computation logic happens outside of that.
Okay, so that's a very good tip. So pretty much like what you can do is extract the minimal part that needs to be locked to its own function and use this pattern there. Exactly. Another gotcha with mutexes that you need to know is that locking twice is bad, and it depends on the system. Some systems allow you, if you already have a mutex, you can lock it again and nothing happens. In Go, this isn't implementation. If you're going to lock twice, you're going to be stuck forever. So don't lock twice. And another form of mutex which is useful is read-write mutex, and it's useful in the case where you have many readers and few writers. If you have equal readers and writers, just use a regular mutex. But if you have a case where many people read, many goroutines read, and very few write, then you can improve performance because it has the idea with the read-write mutex is that only one writer can write lock the mutex, and multiple readers can read lock the mutex when it's write unlocked. Okay. Cond. I mentioned cond before. Cond, I think, is the third useful primitive, and it's used for waiting for an event or announcing when it occurred. Okay, it's also in the sync package. The API is very simple. You have cond wait. It's kind of a condition. You wait for a condition or an event, and it will block until the event happens. And you can have multiple listeners trying to wait on this event. And you have signal, which will wake up a single waiter, and you have notify, which will wake up everybody. So it's kind of like the idea we saw before that you can do with channel closing. But the thing to remember about cond is that the API sucks. Play with cond, just see if you can just read from the README in the Go docs if you understand how to use it, and I assume that you won't. It's very non-intuitive, unlike the others. And I think cond is actually, I think that why I present here is because many people need the broadcast pattern, and channels don't give you broadcast, and mutexes don't give you broadcast. So cond is useful, but I think the second realization that they had is that cond is not really useful. Everything you can do with cond, you can do with closing channels, and I recommend that you don't use cond. Use closed channels, it's much better. I think there is even a proposal to remove cond from the sync library in Golang version 2, because everything you can implement wait by reading from a channel, signal from writing into a channel, and notify by closing the channel. And it's much better. And the main reason it's better, it's not because it's simpler and uses a primitive. It's better because you can also use them in select. And as we said, we don't want to wait or block not in a select in production, right? Because then you may find yourself blocking forever, and you usually don't want to do that. And the problem with cond and the problem with mutex, by the way, is that both of them are not selectable. Only channels are selectable. And that's why I wrote channels in the beginning twice. Always try to use a channel, okay? Because channels are selectable, and you can do the tricks we talked about with timeouts and graceful shutdowns. What if you really want to use a cond, and you still want to have all the beautiful select stuff? What would you do? You would wrap it in a channel. Kind of disgusting, but you can do it. Okay, because many of you come with knowledge of Node, and Node, I think, is relatively similar to Go in a way, in terms of the productivity and how fast you write code. And a lot of people, when they come from Node, they have the mentality of looking for async functions. Okay, async functions are a very popular pattern in many languages, specifically in JavaScript. In JavaScript, they're so popular because you have one thread, so everything has to be async. So, are you having an itch for an async function? So what is an async function? An async function is a function that does not block. So it returns immediately, and it lets you know in the future, in some sort of mechanism that we can discuss, when it completes. So let's say we want to read from an HTTP server, and that read is going to take 5 seconds. So a common pattern in many languages is to have an async function that returns immediately, and once the read finishes, we complete the sync operation and notify our user somehow. So how would you translate that to pattern in Go? Okay, it's a very popular pattern, especially in JavaScript. So, usually in this pattern, you have different mechanisms to notify when the operation completed, like callbacks, promises, async await. So where do they fit in inside Go? Okay, this is the question. And the answer is they don't. Okay, you don't need them, don't use them. Don't implement async functions. I think this is the main takeaway. Normally, all functions in Go should be synchronous and block. That's the paradigm. So what happens if you have a long-living operation, for example, and execution cannot be blocked? So if this is the case, you just need a Go routine. Do this operation on a new Go routine. Go routines are cheap, just create one. With threading, it was always expensive. So you always, did the math. Like, if I want to do something efficient, let's try to keep the thread count as small as possible. Here, don't. But let's say you really want to have an async function in Go. How would you implement it? So one of the patterns is to return a channel immediately and use that channel as the way to communicate when the async operation ended. So the function would return immediately, and once the function finishes, it will probably have its own Go routine inside that does something asynchronous, and once it finishes, it will write to a channel, and the user that received the channel immediately, whenever they want to block and wait, they can just block on the channel. So this is a way to translate async functions to Go, but don't. And the last thing we're going to discuss is contexts. We mentioned context a few times before, and context is, before we say what it is, we're going to talk about why do we need them. So the idea is when you want to pass caller intent across an API boundary. For example, let's say you have 2 microservices or even 2 processes, and you have one caller and one callee, and the caller wants to pass some intent with a call. And I'll give you an example what this meta intent can be. For example, it can be, handle this request for me, okay? But I may want to cancel it in the middle. Okay, for example, let's say that somebody wants to do graceful shutdown to me. I don't need the response anymore, so I want to cancel. So you're kind of like trying to do that thing now, and I want to cancel it midway. So this is an intent that is on top of the request, okay? A different intent can be, handle this request for me, but I'm giving it a deadline of 3 seconds, and if you can't complete it within 3 seconds, I don't want you to complete it at all, okay? So this is another intent. It's a meta intent on top of the request. Where is it useful in Orbs? So we'll circle back to the example that we already gave. So we remember our example before, consensus context asking transaction pool for exactly 100 transactions. So this request may take time because transaction pool may not have enough transactions. And consensus context may cancel in the middle if it needs to shut down. For example, somebody terminates the service or restarts it, or consensus context can give the request a deadline of 3 seconds. And this is actually a real case because in our consensus flow, in the consensus algorithm, usually you have time slots where a leader can respond and propose a block. So you want to have a block with as many transactions as you can, but you don't want to miss your slot. So you can have a deadline which is time related. So how does it work? The caller. I'm not going to show the API. You can see the API by yourself. It's more important to understand the idea. So if you're a caller and you think you want to pass this intent, okay, and you don't have a context already, so you can just create a context. There's API to create a context, and you can indicate on creation if you want to add optional cancellation to this context, so it can be canceled at any time by you. And you can indicate if you want to have a deadline, for example, with timeout or with deadline. It depends if it's relative or absolute, the time. So you create this context, and then you're going to send it to the callee. If you were given a context, for some reason, let's say somebody gave you this intent that they had, okay? And you're a caller, you want to call somebody else. So if you already have a context, instead of creating a new one, propagate the context that you already have. Or if you want to add your own indications, for example, you want to add your own cancellation to it, or you want to add your own timeout to it, so you want to pass it to somebody else, you can just wrap it, okay? It has wrapping mechanisms that you have kind of a parent context. Another important thing is don't store contexts in structs, okay? They're very volatile. They're not transient. They're not supposed to be stored in memory. So the pattern usually is that the first, if you want to pass, if you decide that contexts are the right mechanism for you, so the idiomatic pattern is to pass context CTX always as the first argument of the function. And if you want to call somebody else, you have a context if you received one as the first argument. Like, if you didn't receive it in the first argument, don't pull it from somewhere. Don't pull it from a struct. Don't pull it from state. Okay? So if you want to make sure that you have a context from somebody else, make sure that you receive it as the first argument in your function. So always pass context around like this. How does it work from the CALLEE side? Okay, the CALLEE is transaction pool that has received the intent from context, from consensus context about that deadline of 3 seconds. So the CALLEE would receive the context as the first argument of the function. So when you do a blocking operation, always select. Why? Because you need to respect the intent of the caller. So use a select, and in the select, also one of the channels that you read from is context.done. Okay, this is a channel that lives on the context, and whenever, if you reach the deadline, or you reach the timeout, or you reach the cancel, somebody canceled it explicitly, then context, this channel will be closed. Okay, so if when you select, you read from multiple channels, if this branch of the select returns, that means that the context is terminated. And that means that you should probably shut down and return early to your caller and respect their intent. So this is one way to implement that. Another thing is if you call somebody else, like a different service or somebody else who may block, you want to propagate the intent of your caller to them. That's why you need to propagate the context. Why? Because they may block, and if you receive the deadline, you want to pass that deadline forward. So it works very, very nicely, not very complicated. Yeah, I think that's it. One of the things about context is that we're considering right now, actually, is to add a context to all the methods in the system, in all the services, making out orbs. But because it's a lot of boilerplate, we have not decided to do it yet. So we're looking into different ways to implement the same intent passing deadline system. And if we're going to find a way that has less boilerplate, we're going to use it. And if we don't, we might find ourselves adding contexts in the code generation from the protos to pass context in the system all around. So this is an open issue for discussion.